So what is tensor and how it will be used for the calculation of this tensor? We'll go through this. First, we'll go for some simple mathematical calculations. Then I'll tell you what we are actually meant for. See this. There are some directions. This is x1, this is x2, and this is x3. This is some directions. Three directions is x1, x2, and x3. And there is a vector quantity that is called as S. There is a vector quantity. See, this is a vector quantity that is called as S. Okay. What is that value of that S? What will be value of that vector quantity S? How can you write that vector quantity S? So S can be written as in that format. S is equal to all the components, vector addition of all the components in all directions, s1 i1 plus s2 i2 plus s3 i3. This is the method how we write a vector quantity. What is that i1 i2 i3 here? What is that i1 i2 and i3 here? Just tell me what is that i1 i2 and i3 here. In vector quantity, what are these I1, I2 and I3 means for? What does it mean for? I1, I2 and I3. If this is then you tell me in mathematical calculations, what does it mean I1, I2 and I3? This I1, I2 and I3. What does it mean? What is I1, what is I2 and what is I3? The I1, I2 and I3 are the unit vectors. All these are the unity vectors. Unity vectors. All these are unit vectors. In the respective directions. In the respective directions means x1, x2 and x3. What we have seen in the figure. That we are taking three directions x1, x2 and x3. So these are the unit vectors in the directions of x1, x2 and x3 respectively. So, in accordance with the convection and convenience in working with the tensor quantity, the coordinate axis will be designed x1, x2 and x3. So, we are not taking x, y, z. So, for the easy of the calculations, so we are taking that x1, x2, x3, where x1 is equivalent to our previous designation x, x2 is equivalent to, we are not taking that x, y, z because for the easy of the calculation, but you can tell that x1 is equal to x, as x2 is equal to y, and x3 is equal to z. These are the directions. These are the directions. So we can take this in that format also. Then what is that S1, S2 and S3 here? This is the equation. This is the equation. In equation we have S is equal to total vector sum of the S1, I1, S2, I2 and S3, I3. So I1, I2, I3 the unit vectors in the respective directions of x1, x2 and x3. Then what is that S1, S2 and S3? What is that S1, S2 and S3? S1, S2 and S3. What are they? S1, S2 and S3. These are all are the components of total vector S. Component of S in x1, y1 sorry x2 and x3 direction. Okay, these are the component of S in the total. We are taking the total vector, that is S. These are the components of S. Okay, in the directions of, that is, some directions are changed here. In the directions of so x1 dash, x2 dash, and x3 dash, all are dash. x1 dash, x2 dash, and x3 dash. Okay, these are the component of S in the x1 dash, x2 dash, and x3 dash. So where we can represent the x1, x2, and x3 then? So see here, see this figure, where we can represent the x1, x2, and x3 here in this figure. For that, we will show you where we can locate this different axes here. See, this is this is x1. I can say this direction is x1 dash, x1 dash, and here the we have sorry, there is some. No, that's right. Here it is S1. Here the total stress is S1 in x1 direction, and that is S2, and that is here it is S3. These are component S1, S2, S3 are the simply components of x1 direction, x2 direction, and x3 direction. So I have to make some corrections here. So let's see that. Go to the previous equation. So it is only. Sorry. Okay. So another thing is that we want to find out the component of S refers to if you take the different directions like x1 dash. If you are going for the, if you have interest in find out the component of S in different directions, so that is x1 dash, x2 dash, and x3 dash. We have to, our interest is to find out the components of S, component of S, component of total S in respective directions. In respective directions. In respective directions. So, to calculate the different components of S in the respective directions, so we have to represent the different directions here. We are going to representing the different directions. I am showing you the directions here. See here, that is see this is S. So x1 direction, this is S1 dash, and this is when some axis, when I am rotating this axis now, when I am rotating this x1 axis, the similarly at the same time this x2 axis will be also rotated in clockwise manner. I am rotating this x1 axis in my clockwise manner. When I am rotating this x1 axis in the clockwise manner, this will be the distance from this will displace from x1 to x1 dash. The axis is now displaced from x1 to x1 dash. Similarly, at the same time, the x2 will be also be displaced. So the displacement in here, that in x2 direction, is that like that. That is x2 dash, x2 dash, and here the component is stress component is s2 dash. Here the stress component is s2 dash. So now here we have to calculate the component total stress in the displaced directions. Now we are going to calculate the total stress in the displaced directions. For the calculation, what we'll do here? Total stress in the in these directions. Total stress on all these directions. So when you're going for the calculation of the different directions, so here the component of the vector will be changed. Component of the vector that will be also mutual. Don't talk during the classes. So if you have any problem, then you can mute. Okay. Don't talk in unmute conditions. So here we have to go for the calculation of the component of S in the displaced direction. So displaced direction, the component will be written as S1 dash. Sorry, it's S dash na. Sorry, we'll write if you write calculation for the S1 dash na, what will be the value of S1 dash? S1 dash means the displaced position. This is the S1 dash na. There it will be S1 dash. It will be S1 dash here. See this is the S1 dash. So we have to need to calculate the values of S1 dash here. So how can you go for the calculations of the S1 dash? How can you calculate S1 dash now? How can you calculate this S1 dash? The vector component by displaced axis from x1 to x1 dash. So if you see here that it will look simply the cos component of S1. It will simply the cos component of S1. We can write down that S1 is equal to S1 cos theta. Cos theta, you don't know the theta value, so theta will be in between x1 and x1 dash. That will be the value. So we can write simply S1 is equal to S1 cos x1 and x1 dash. This will be the value of this will be the value. Again, at the same time, when we are calculating the x1 s1 dash, this axis will be displaced. X1 is displaced from x1 to x1 dash. Similarly, the x will be also displaced from x2 dash. So there will be a cos component will be must be there. So here further we will also calculating this the s2 cos x2 and x1 dash. X2 and x1 dash, the displaced by the x1, the displacement by the x1 dash. Similarly, you can write down the s3 cos x3 into x1 dash. This is a simple calculation, mathematical calculations. This is a simple mathematical calculations. How can we calculate the component if the axis is displaced from one position to the another positions? That will be the cos component of the each component, each the previous components, cos of the each previous components. So it is very simple to write down this equation. So see this equation. See this equation. I am going through this equations only. See, I am writing this equation in the new format. I am going to write this format equation in a new format. See this equation I am going to write is here. The S1 dash is equal to U. I can write here A11 S1 plus A12 S2 plus A13 S3. So, is there any difference in the equation? This equation, this is if I am telling that this is equation 1 and this is equation 2, what is the difference in these equations? What is the difference in these equations? We are just replacing this the x1 and x1 dash, x1 and x2 dash, x1 dash and x2, x3 dash and x3. So this cos component or cos component, all these cos components are replaced by a1. Just a minute, why it is happening here. See, these cos components are just replaced by these new components. All these cos components are replaced. That cos x1 and x1 dash, cos x1 and x1 dash is replaced by a1, a11. A11 means what? Cos A11. That is cos A11. A11 means 1 is x1 and x1 dash. X1 dash. Sorry, I'll just remove it. The direction cosine, this A11 means the direction cosine between x1 and x1 dash. It is the A11 means the direction cosine. Simply, if you are telling A12 means what? X. A12 means what we will write here? X1 dash and x2. the direction cosine between the x1 dash and x2. Similarly, a13. 13 means x1 dash and x3. So if you are writing in that format now, so it is very easy to remember. Instead of writing this cos x1 x1 dash, cos x2 x2 dash, sorry, x2 x1 dash, cos x3 x1 dash. So this is a very simplified format to writing the replacing this equation in that format. The equation 2 is now very easy to write that. The s1 dash is a11 s1 plus a12 s3 and a13 s3. Similarly, if you are talking about this is the stress by, yes, sorry, this is the vector by calculating this component in one direction, we are replacing one axis only. Here we are replacing one axis only. The axis is rotated is only x axis is rotated x1 dash. If we again replacing the x2 axis, na, similarly we got the equations for s2 dash. Similarly, we got the equation for x2 dash. So what we will write, what will be the format of the equation we will write here? Can you tell me? What is the format of writing the equations here? So if when we are calculating for s1 dash, we are writing a11 because it is starting is 1. Here we are going for the s1. So we are writing a1. Everywhere the a is started with the subscripts of 1. So here we will what we will do? Now we will start with the subscript of 2 because it will written as 2 s2. So again we have 2 a21 s1 plus a22 s2 plus a23 s3. Bujhipalla? Have you got that? Have you got that? So similarly, if you writing the s3 dash, if the axis third axis is x3 axis is rotated, so what will be the value we can write here? The a31 s1 plus a32 s2 plus a33 s3. How simply you can write here? How simply you can write here? See this. We are don't going for this complexity in the format of in the form of cosine components. So it is very easy to write. Now we can write this s1, s2 and s2 in a simplified format also. If we try to write this in a simplified format, na, it is very easy for us now. See here, this is s1, s2 and s3 also. So if you write in a simplified format, how to write this in a simplified format? See this. How we will write this in a simplified format in equation 1, equation 2 and equation 3. So we note that the leading suffix for each direction cosine in each equation is the same. The leading suffix. Leading suffix means the s2. When we are writing the s2, we are using a2, a2 here, a2 here. When we are writing 3, s3, where you have the a3, everywhere is same. So only the second quantity will be changed. Only the leading quantity will not be changed. Only the second quantity is changed. So you will try, if you try to write down this in this format first also. See this, s1 dash is equal to summation of j is equal to 1 root 3 1 2 3 and that is a1 sj. So we can write that in format. If I say that a1j, if I writing a1j, that means I am writing in every step I have going for the a1 j1 a11. If I putting this equation a11 s1 plus a12 s2 plus a13 s3. So you can simply write this in this format, aij format, a1j format. So similarly you can write this equation also. The second equation can also be written s2 dash is equal to sum of I is equal to j is equal to 1, j is equal to 1 2 3 a2 sj. This is the writing of equation in that format. Similarly, you can write the s2, s3, s3 dash also. J summation of j is equal to 1, 2, 3, 1, 2, 3, 8, 3, j. The leading suffix will be same. Everywhere the leading suffix is same. See this equation clearly. So we can now simplifying this long equation. What is written in the format s1 cos x1 dash, s2 cos x2 x2 x1 dash plus x3 cos 3 x1 dash. This long equation now it will be derived to two statements. How easily it can be written as by this format. So again we can, if you want to, if you want, then again we can also modify this equation. So how will modify this equation? See this again, how to modify this equation. See here again, how will modify this? We will modifying this like that. We will putting that I here, we are leading, we are using the leading suffix everywhere, a1, a2 and a3. If you are replacing this leading suffix is equal to I is equal to 1 2 3, then the equation will be very much easy for us to write that. So combinedly, if we are writing si dash, we are now replacing this equations si dash. Si dash, what is si dash? Now summation of j is equal to 1 to 3, that is aij, aij and sj, aij, sj. In bracket, what I am writing here? In bracket, I am writing here that I is equal to 1 2 3. Now this is the full-fledged equation, that is equation 5. Now it is understandable by you? Is it okay for you? So if you this is now this complex equations, all these complex equations are now derived in a simplified format. So you can replace here, you can write here in that format also ai1. If you are putting only the j, if you are by summation, by if you are putting in the values of j only, s1, so ai 2 s2 plus ai 3 s3. Now we are putting only the values of j. If you are start putting values of I, then it will be very easy for us to rotate every notation. So what is I am writing just one equation. I in place of I am putting writing the s1. So here in place of I also I am writing one s1. In place of I am writing one. Now the equation is in that same format. The whole equations, the total equations what we have derived there, the displacement of the axis from one position to the another position can be easily returnable in that format. So we can say the equations can be, again we can write these equations in the format like that. This equation, so we can write in the format is that very simplified format, that is si dash is equal to aij sj. This is the format of writing the equation. This is equation number 6. This is equation number 6 now. Okay, this is equation number 6. So how easily we can write the displacement of one vector from one axis to another axis, the displaced axis. So the suffix notation is very useful. That's where what we are using here, the suffix notations, the ij. It is very useful. We are just replacing everything by ij. So that suffix notations are very much important here and is useful also. The expressing any systems, for the expressing of the systems of the equation usually found in continuum, that is in continuum mechanics, in physics and mathematics also. It is understood that when suffix occurs twice in the same term, in case of the suffix j, it indicates summation with respect to that suffix. If that suffix appears twice, that means it will be summation. Unless otherwise indicated, the summation of the other index will be from 1 to 3. I here we are using the two suffix. One is the I, another is the j. We are using two suffix. One is I and another is the j. I is called as the free suffix. I is called as free suffix. I is called as free suffix. Because it will be expanded. If you are putting the values of I, it will be, the equation will be expanded. So it will be, that's why it is called as the free suffix, and j is called as the dummy suffix. J is called as the dummy suffix. J is called as dummy suffix. So these A and J, I and J will change the whole equation writing systems. It is only purpose to indicate the summation. Exactly the same three equations would be produced if some other letters were used in dummy suffix. So if we are using any dummy suffix, there are two suffix. One is the free suffix, other is the dummy suffix. In place of J, we can write R also. If you are writing R, your equation will be like A I R S R. So you can write anything in the dummy suffix. So what will happen here? That the complete determination state of stress at a point, that what we have derived in that equation 2. Equation, that completely determination of state of stress. These conditions, this type of equations are very much used into determining the state of stress at a three dimensional state of stress. As we see that there are 9 components, I am already told you, in three-dimensional state of stress there is 9 components. 9 components means 3 components of stress and 6 components of shear stress. There are generally the 9 components of the stress on the orthogonal face of the element at a point. A vector quantity only requires the specification of 3 components. That vector quantity will represents only 3 components. Obviously the stress is more complicated than the vector. If you are comparing the stress with the vector, the stress is more complicated than the vector, because we need 9 components and there are 3 direct stress components that will be required to be derived. So physical quantity that transform with coordinate axis in the manner of the equation what we have right here in the equations are called the tensors. These are called the tensors. The manner of writing this equation, just that equation we have derived previously, that is called the stressor quantity. So just writing here, just wait, I am writing that equation. I just deriving this, just writing these equations. The equation which is already we have derived, the sigma is equal to, in three-dimensional state of case, sigma x L square plus sigma y m square plus sigma z n square plus 2 tau xy lm plus 2 tau yz mn plus 2 tau xz ln. So this equation is called the tensor equation, stress tensor. This type of equations are called the tensors. These type of equations are called the tensors. Equations are called the tensors. And the stress, you have to remember that stress is always a second rank tensor. Second rank tensor. Stress is a second rank tensor because you need 9 components to derive, to mention the stress. We need 9 components. See here, this is component number 1, component number 2, component number 3, component number 4, component number 5, and component number 6. These are the simply 6 components are here. Also the tau yx is there, tau that is 7, tau zy is there, that is 8, and tau zx is there, that is 9 components. We need generally 9 components to specify the stress. That's why the stress is called a second rank tensor. Remember, the stress is a second rank tensor. The stress, strain, and many other physical quantities are the second rank tensors. Remember, this stress, strain, and many other physical quantities are second rank tensors. Yes, then what is the scalar? We are representing the stress as a vector. So, what is that scalar? Scalar quantity which remains unchanged with transmission axes. Here you see that when we are changing the vector from x1 to x1 dash, the quantity will be changed. That's why it is the stress will be also changes by changing the directions. So it is called as the vector quantity. The scalar, what is that scalar? The scalar means the quantity remains same, that cannot be changed with the transformation axis. So scalar requires only a single number its specification. Scalar requires only one specifications. It does not require any other specifications for this. So scalar tensors are zero. The tensor of scalar quantity is zero. The tensor of a scalar quantity is zero. Stress is a second rank tensor, and the scalar has zero tensor. Scalar has zero tensor. Zero rank tensor. Zero rank tensor. Stress is a second rank tensor. Scalar is a zero rank tensor. Vector quantities. Remember this what I am telling you. Vector quantities require three components. Vector quantities require three components for their specification. So in the calculation of vectors, what we have calculated now S1 dash, S2 dash, and S3 dash. So vector quantities require three components for their specifications. So the tensor of the first rank. Vector has first rank tensor. First rank tensor. Because it requires three quantity. First rank tensor. So the number of components required to specify quantity is 3 to the power n. So how can you represent the rank of a tensor? How can we represent the rank of a tensor? Rank of the tensor is simply represented by 3 to the power n. N is the here n is the rank. N is the rank. Put here n is equal to 1. N is equal to 1 means the total quantity we require is 3. That means vector has first rank tensor. So if similarly, if we put n is equal to 2, so what we find here? Now when we put n is equal to 2 here, the component will going to be 9. So stress is to specify stress we need 9 quantities. So stress is a second rank tensor. So in that format we will show the ranks of the tensors. And another important thing that all the elastic constants that relate stress with the strain in an elastic solid is a fourth rank tensor. Elastic constants. Elastic constants are fourth rank tensor. Fourth rank tensor. Elastic constants are fourth rank tensor. That means if you put the values of 3 to the power 4, n is equal to 4, so what will be got? 81. That means to specify the elastic components, we will need 81 components. We need 81 components in the general case. That's all for the today, the rank and the tensors. Next class we will be presenting the stress. Here in this class we are how do we show you? We show you the vector quantities. Next class we will show you. I will going to show you the stress quantities. Okay, till then.